And will that be like on the FPGA board?
Mm-hmm. Yeah, one of the problems on the IPGA. That's right. Simulation is just too dry, too boring. So basically the entire lecture's time, okay, 85 minutes. So the problems are decoders. Oh, first, structure, right? Or model method. So pay some attention to the parity bit generation. So the parity bit generation and checking logic, what is it? Just XOR gates, right? If you did the homework assignments, if you want to check if there are odd number of ones in the message, you do XOR logic with all the bits. If you are getting a 1, what does that mean?
If it's
So-
even parity checking, that means it could be.
Yeah, so if you have, for example, 0, 0, 1, 0, 1, doesn't matter, okay? It's just even number of ones. If you XOR all these digits, you're getting what?
You're just going 0. It'd be 1.
Wait, 0, right? 1, 1, 0.
Oh, okay, yeah.
It's distracting you because this looks like a little face. What's the result here?
0.
0. Then 0 XOR 1 is what? 1. 1 XOR 1, 0 is what? 1. 1 XOR 1 is what?
0.
Yeah. So if you have even number of ones in the message, if you XOR every single bit, you're getting a 0. I just give you one example, but if you can add more ones to it. But eventually, if you have an even number of ones in the message, you're getting a 0. Okay, you're getting odd number of ones in the message, and as a result, if you XOR every single bit, so the result becomes 1, right? Okay, so if you just remove this one, change it to 0, so eventually you're getting a 1. Keep that in mind, okay? It's a conclusion you should directly use, okay? Since it's closed book, closed notes, so you should know this before the midterm. And also, you need to know the IPGA. Since internet is not allowed, right? So you are not supposed to search in Google or looking at my tutorials. So eventually, you need to know all these decoders code, right? So that the 7-second display. From A to G, right? Which is A, which is G. It's following a certain order. Let's take a look at it really quick. It's here. So starting from A, right? Doing this. And reach here is G. It's A, B, C, D, E, F, G. Okay. So it'll be a very simple display module, right? So doing some sort of calculation and display it. So you have to write a top module for it and modify the sub module which is provided in the exam, and verify it on your FPGA board. Okay. So bring your FPGA board and bring a phone which is able to record the video, the demo video. If your phone doesn't work really well, maybe you can use your laptop's camera. All right. Only 3 problems, 85 minutes. Simulations and FPGA demonstrations. So FPGA demonstration is the very last problem, and I need to record a video of it. Okay, but for the simulations, just show the simulation waveforms and make snapshots. Eventually, everything should be turned in to canvas. Any questions on this? It's next Thursday, okay? Midterm exam, taking 10% of your grade.
So it's 3 problems.
Yeah.
We have the whole class time to do it.
Yeah.
And then hierarchical structure, that's like modules, correct?
Yeah, just modeling method, right? We have learned structural, behavioral, and what's the next one? Yeah, the data flow, and yeah, and then hierarchical, right?
Yeah.
Yeah, so this one, it's like the first system, right? You instantiate submodules in your top and use that top as a final chip, and then include the top module to simulate that top. I mean the test bench to simulate the top. Okay? We had a quiz on it, so nothing is going to will be beyond the quizzes and homework assignments. It's actually easier than the quizzes. Okay. So now let's take a look at the lab for today. So we were at, let's see. We're trying to finish the display module of the coding. That's coding of the display module. If you look at the notes, I hope I have the notes here for you guys. Here. This one, right? Okay. So that's for task 1. And I already probably typed 80% of the code last Thursday for you guys. So the adder is almost done. And we were in the progress of typing or finishing up this display module. So you can see that the adder did all the operations, and we derived all the logic expressions for the adder. Remember the overflow indication bit, the digits, the C2 final, all these kind of things. And eventually, the adder is in charge of delivering the 4 final results, the 4 bits. Okay? So now we have the final results, the 4 bits. But the problem is the final result is in 2's complement. It's in 2's complement. So that is why we need it's sort of like a lookup table. The case, right? All different cases. If you see this case of the 4 bits, you want to display what? Okay? And since we know, if we see a like 1, 0, 0, 0, since we know it's minus a, so we are going to display a 8 an 8 at the 7-segment display module, and we have to throw a minus sign in front of it. So that's how it works. The same very similar principle for all the rest, all the other numbers. Okay, and so first of all, your display module has to receive that 4-bit input and then translate it into the 7-segment display LED pattern. And depends on like which bit, because you have 2 bits, you have 2 units to display the number and the sign. Okay, so if your AN 4-bit AN controller is scanning through the 2 bits, right? If it's activating the second one from the right, then you are trying to look at the MSB to see if the negative number or positive number in order to display a sign or a bar or nothing in front of the number. Okay, so we don't need to add a plus sign in front of it. So if the positive number, then just display nothing. Okay, if it's activating the LSB of the 7-segment display unit or the one on the right hand side, then you are looking at the numbers. So you put your decoder in it as a case statement unit. And that is why we have these 2 pieces of codes coded up last week. You can see here is the adder. Okay. Still remember the adder structure. So Friday gave you this carry in, extra A is getting AA, right? And C0, S, also S, overflow indicator, C final, and digit equals C final concatenated with the S. So the adder module is pretty simple. It's pretty simple. Eventually, it's just giving out these 4 digits in this digit vector, okay, which is here, right? Digit. Now let's move to the display module here, right over here. So this module receives digit. You can see it has an input digit. It receive it, and then you need your clock to update the output at the AN 4-bit of the AN vector and the SAG, which is the output pattern for the LEDs. So we were at here. Let's see if we can recall what we were doing over here. So if while we're counting, just really quick simple question, while we're counting,
So it's not too fast for us.
it's not too fast for us, yes. So this is counter for, what is this counter for?
Cycling through each like digit on the 7-second display, or like each character.
Yes, activating each unit, right?
Yeah.
Going back and forth. So this cannot be too slow. It doesn't like the counter max for the LED, the running LED, which is 1 second. It takes 100 megatimes to reach the count max. So this one should reach count max pretty quickly. So you can see the count max is about 64,000, but you are able to count up to 100 million a second. So it's basically scanning back and forth to let your eyes not be able to resolve the blinking, right? So this count max is for that scanning for the 2 units, and whenever it reaches count max, what we should do is first we should activating the other one. Okay, so that's the first operation, and then we need to clear the counter. Okay, but during that process, so before you swap the activated unit of the 7-second display unit, you need to know that where you are at right now. So if you are at the sign unit, you are doing something different. Because if you're scanning the, let me grab the picture here. You got 2 units. Okay? So basically it's doing this, right? If it's activating this one, activating this one, so we have to add a condition in the if statement, so which means whenever this one is getting activated, okay, and the count reaches count max, then what we want to do is throw a sign to it, right? Depending on if it's a positive number or negative number. So if it's activating this one, then we just throw the seg to this unit. So if you look at the code here, when an1 is 0, an1 is 0, which one is an1? So the sign bit is an1, right? So if this guy's 0, I don't need to give anything to it, right? It should be this pattern. So all the LEDs should be off. All right, what's the other condition? Oh, sorry, when this is activated, and also this is a native sign, right? Native sign. So I need to add a bar to it. So right after that, I should swap the two units. So previously this one was activated, but now I should activate the one on the right hand side instead. What else do we need? For every case, there will be like a bunch of cases. Could be 1, 2, 3. So this is one of the cases, which is adding the sign to it, right? So first we need to clear a counter, makes sense. Second, we should swap the two units, okay? Because this current condition is activating the sign location. So when we are done, we should swap it. Should activate the other one. So whenever it reaches this clock rising edge again, it's able to deal with the number unit instead of the sign unit. And definitely we need to throw a data to it, to the seg. Okay. What else do we need within that if statement? There should be something else there as well, I think. What else? So ANN is the intermediate register. The reason we want to use ANN as a temp, right? Temporary data in the middle, is because when we are doing this shifting bits, and if we directly use AN, which is have a direct connection to the AN keyword of the top, it won't allow you to do the shift. It's really interesting. So we have to get a buffer before that AN here. So we do have AN, okay? So in your top, in the instantiation, your AN in the sum module is directly shorted to the AN keyword in the top module. They are directly shorted. Okay? So you can treat AN here as the AN of the top. So that is why this AN here cannot be shifted. It just doesn't allow you to shift it, doesn't like it. So that is why we need an ANN, which is the intermediate register in the middle, right before that AN, to do all the shifting. Just let you guys know. So in that case, if you draw it on the paper, it looks like this. So this is your IPGA top, AN of the IPGA. Okay, and our sub module, AN here. It's 4 D flip-flops. Have a direct connection to the AN of the IPGA. So if they have a direct connection to the IPGA, they are equivalent. So which means the AN here is basically the AN here. All right. So the thing is, it doesn't allow you to do the shifting. It's gonna report errors. So that is why you need another level of latch. So you can do all these operations, concatenation, whatever. Okay. So this is called ANN. All right. So come back to the code. In that case, what else do we need? One thing I didn't talk about too much, I think, during the semester. So for hardware modeling, it's different from C++. So we have learned C++ a lot, and they are instructions stored in the instruction memory. So the instruction pointer will take out every instruction once a time. Okay, just following a certain order from top to bottom, and then loop back to the top. But hardware is different. After you implement this one to the hardware, it's already implemented. It's like a digital circuits. It's not executing from top to bottom. It's immediately being implemented on the hardware once. All right. So the way you are running something a certain order or a certain sequence is using a clock to do all the updates. But everything will be implemented. There's no instruction. It's everything is just hardware. Okay, that's why it's called hardware description language, HDL, right? HDL. So in that case, this one is getting updated. This one's getting updated, but the thing is, ANN is not exactly ANN, right? If you look at the structure here, this one getting shifted, but the thing is, you still need to assign everything to ANN here. Okay, you have to still assign ANN to ANN. Otherwise, it's just shifting within itself. It's not being sent to the port. So what else? In that case, what do you need over here? What do you need over here? What is start a new line after it?
Like,
Lowercase o, right?
yeah. Yeah.
Okay, so we should do that. What else? So the SAG, if you look at the SAG here, it has 7 bits. 1, 2, 3, 4, 5, 6, 7. 7 bits for the SAG data. If it doesn't include the DP. So if you don't give anything to DP, the DP will be a very dim LED, which looks bad. So we want to turn it off. So how to turn it off? It's actually common anode, right? So it's actually 1 will turn it off.
Oh yeah, that's fine. That's right.
So it's a 1 binary bit, and the value is 1. Okay? So it satisfies this condition and comes into this condition. And doesn't satisfy other conditions. So in that case, in every condition, you have to include all these assignments to make sure the hardware is working properly. You don't want to just include it in one of the conditions and eventually you believe it's going to happen for all the cases. Nope, because it won't enter other conditions. But during each time frame, you want the hardware to operate as what you expected. So that's why ANN need to be swapped. After it's getting swapped, you need to assign ANN to ANN, right? And also DP need to be turned off. And DP is a keyword. You can see I do have a DP here. Since DP is not getting, shifted or swapped, so it's fine. I don't need an intermediate register in the middle. So directly, I'll assign a 1 to DP, and DP will be directly shorted to the DP of the top, which is the keyword, a physical LED on the board. Okay, so this condition is already covered. What about else? So you can see I'm still looking at the sign bit because ANN1 is still 0. So which means the sign bit is getting activated. So this guy is still activated. I'm not done yet because I just covered the negative case, right? The negative case. But also it could be a positive number. So in that case, ANN is still 0. However, your MSB of the digit becomes 0, right? So now it's a positive number. It's a positive number.
It should just be on.
What should you do?
Just turn.
Try to recall the vim command first. Shift V, right? Then what? Y?
Yeah, one.
Then what?
And then it would be,
Actually P, right?
yeah.
Keeps going like in and out.
Oh, the projector?
Yeah.
Sorry about that. Yeah. I'm wondering if it's my laptop's issue or the projector's issue. How many times has it been like that? All the time? All the time?
No,
No? 3?
it just started.
Or just started?
No, it happened before too.
Yeah, something need to be updated, right? How to delete the line? DD? Okay, so what do we need to change over here? So frustrating. So when I had a VGA port of my on my old laptop, it worked perfectly. I don't know why HDMI is having issues. Keeps having issues. What's this one? Mm-hmm.
For today's quiz, do we need to know like the logics
Mm-mm.
for
No. we can probably work on the code after the quiz, because the quiz is just a very simple 2's complement. There's nothing with a circuit and coding. So I can take time to try to fix it if I can. I'll give you 15 minutes to work on it, right? Very simple calculations. Keep in mind that overflow only happens when you have a PPN or NNP, but nothing else, okay?